This is Lesson 21 in our Calculus 2 series, Work. You might have seen work defined in physics class as force times distance, and this is true when the force is constant. If the force varies as the position of your object varies, then we can consider the force to be f of x, a function of the position x. And so, for example, if x is going from A to B, the total work can be approximated by dividing this interval into n subintervals, as we usually do. So x0 is equal to a, xn is equal to b, and xi is equal to a plus I delta x, where delta x is b minus a over n. And then our total work can be approximated by the summation f of xi delta x. So on each subinterval, we're considering the force to be constant, f of xi, and the distance traveled is delta x. Now I'm sure you know what's coming next. This is just an approximation, and of course we want to take the limit as n goes to infinity. And so that is going to give us the definite integral from a to b of f of x dx. And this is the work to move a particle over the interval ab, where f of x is the force function on that interval. Now the types of work problems we'll see in this lesson will be work to move a particle, work to compress or stretch a spring, work to empty a tank of liquid, and work to lift a cable or rope. So let's start with work to move a particle. For example, a particle is moved along the x-axis by a force that measures radical 4 plus x pounds at a point x feet from the origin. Find the work done by moving the particle from the origin to a distance of 5 feet. So here, as the particle moves, we know that the force is changing with respect to that position. Our force function is given then radical 4 plus x, and we're asked to find the work done by moving the particle from the origin to a distance of 5 feet. And notice that x measures feet from the origin. So this tells us that our interval on x is going to be 0 to 5. So we're integrating from 0 to 5 our force function, radical 4 plus x. And so we'll do a u substitution here. Don't forget to change your bounds to be bounds on u. And here we get 38/3. But we should be careful and talk about the units here. Remember that work is force times distance. And the forces that we have here are measured in pounds, and the distance traveled is measured in feet. So here we have pounds, here we have feet, and so our units are going to be foot-pounds. And so we have 38/3 foot-pounds. Now let's talk about springs. Hooke's law says that the force required to maintain a spring in a given position is proportional to the distance the spring is compressed or stretched. So the force required, so we're talking about f of x, is proportional to, is equal to a constant times the distance the spring is compressed or stretched. So x is going to be the distance the spring is compressed or stretched from natural position. So f of x is equal to k times x. K is called our spring constant. So if our force function is given by kx, then the work required to compress or stretch a spring, d units from its natural length, would be the integral from 0 to d of kx dx. Again, kx is the force function f of x. So just as in the integral at the start of the lesson, we're integrating f of x here. If a spring is already compressed or stretched, c units from natural length, then the work required to compress or stretch it further to d units from natural length is going to be the integral from c to d of kx dx. A common source of error with work integrals for springs is not to have the proper bounds. We want to remember that these bounds are measuring distances from the spring's natural length. So in this case, we're starting at natural length and we're stretching or compressing to a distance d units from that natural length. In this case, we're talking about two non-zero distances from natural length. But remember that the bounds are always distances from the natural length of the spring. So for example, a force of 4 pounds is required to maintain a spring compressed 0.25 inches from its natural length of 1.25 inches. Determine the work needed to compress the spring from the natural length to a length of 0.85 inches. Okay, let's take a look at the first thing that we're given. A force of 4 pounds is required to maintain a spring compressed 0.25 inches from its natural length. This is telling us that 4 is equal to a constant times 0.25. 4 is the force, that's equal to kx, x is 0.25. So that tells us in this case that k is equal to 16, and then we know our force function for this spring is 16x. Now it says determine the work needed, so now we're going to be integrating. Determine the work needed to compress the spring from the natural length to a length of 0.85 inches. So now we're asked to find an integral for work. But just as I was saying before, we have to make sure we get the bounds on the integral correct. Remember that the bounds on the integral are always distances from the natural length. This says we want to compress the spring from the natural length to a length of 0.85 inches. Well, how far from natural length is this? 0.85 is equal to how many inches from natural length? Well, the natural length of the spring is 1.25 inches. That's what we're given. So this 0.85 corresponds to a distance of 0.4 inches from natural length. So that tells us our integral is going to be the integral from 0 to 0.4 of 16x. Again, we were given the force required to maintain the spring 0.25 inches. That allowed us to find k, the spring constant for this spring. So now we know f of x is equal to 16x. Then they're asking us to determine work needed to compress the spring. So we know we're going to be taking an integral, and we just needed to find the proper bounds. From natural length means the bottom bound of the integral will be 0, and then to a length of 0.85 inches, we just needed to write this in terms of distance from natural length. So we subtract the 0.85 from the natural length of 1.25, and that gave us the upper bound for the integral. That's 0.4. So now we're here, and so we integrate, and we get 1.28 inch-pounds. But inch-pounds is not a standard unit, so we really should convert this to foot-pounds. Well, remember that this is multiplication of inches times pounds, so we can replace this 1 inch by 1/12 of a foot. So we're multiplying 1.28 times 1/12, and that gives us approximately 0.107 foot-pounds. Let's take a look at another example. If the work needed to stretch a spring 1 foot beyond its natural length is 12 foot-pounds, how much work is needed to stretch it 9 inches beyond its natural length? If the work needed, so they're giving us work, so they're giving us information about an integral, to stretch a spring 1 foot beyond its natural length, so we're talking about an integral from 0 to 1, and this integral turns out to be 12 foot-pounds. So we're given the integral from 0 to 1 of kx. This is the force function for this spring. We don't know what k is yet. This is equal to 12 foot-pounds. This allows us to solve for k here. And then we're asked to find how much work is needed to stretch it 9 inches beyond its natural length. Be careful, we're in feet here. We've got 1 foot beyond its natural length. We've got 12 foot-pounds. Let's talk about this 9 inches as 3/4 of a foot. Then we're asked to find the integral from 0 to 3/4 of a foot of that function kx. So we need to take the integral that we're given and solve for k. So 12 is equal to the integral from 0 to 1 of kx. So kx squared over 2 going from 0 to 1, that's k over 2. K over 2 is equal to 12. That tells us k is equal to 24. So let's put a 24 in here and find the integral that we're asked for. And we get 27/4 foot-pounds. Now let's take a look at tank problems. We're typically asked to find the work needed to pump the liquid to the top of the tank or even higher. So typically we're going to slice up the volume we're emptying, and then we want to measure the force on this slice of water and multiply that by the distance it needs to travel. So the force on the slice, force is always given by mass times acceleration. To get the mass, we're going to look at the volume of the slice multiplied by the density. And the acceleration is given by gravity. So if we're in the metric system, our volume will be given in terms of cubic meters. Our density will be given in terms of kilograms per cubic meter. And so notice when we multiply that together, the cubic meters cancel and we're left with mass, kilograms. And then in this case, we need to multiply by gravitational acceleration, 9.81 meters per second squared. And so the force then on the slice is going to be given in newtons, kilograms times meters per second squared. If your volume is given in terms of cubic feet, then the density is given in terms of pounds per cubic feet, and notice the cubic feet will cancel. And pounds, keep in mind, already includes gravitational acceleration, so we do not need to multiply gravity in this case. Our force is just given in pounds when we multiply the volume of the slice times the density. So then the work, which is the integral of the force on the slice multiplied by the distance traveled by the slice, is then going to be the volume of the slice multiplied by the density of the liquid multiplied by gravity if we need it, multiplied by the distance traveled by the slice. And all of the tank problems are going to work this way. So let's take a look at a problem. A cylindrical water tank of radius 10 feet and height 30 feet is half filled with water. How much work is required to pump all the water to 6 feet above the top of the tank? The density of water is 62.4 pounds per cubic feet. Okay, let's sketch out the situation. We have a cylindrical water tank of radius 10 feet, of height 30 feet. It's half filled with water, and we want to pump all of this liquid out the top of the spout. The spout is 6 feet above the top of the tank. So what is it that we need to figure out? Our work is going to be the integral of the volume of the slice times the density of the liquid times gravity if we need it times distance traveled by the slice. So let's work on finding these quantities. What's the volume of a slice here? If we slice up our water, what's the volume of a slice? Well, this is going to be a cylindrical slice. So its volume is going to be given by pi r squared multiplied by the height of the cylinder. Well, the radius here of this little cylindrical slice is 10. We were given that's the radius of the cylindrical tank. So we have pi times 10 squared. And then this height here is delta x. So we have pi times 10 squared delta x as the volume of our slice. And keep in mind when we go and put this into the integral, that delta x becomes a dx. So this is 100 pi dx in our integral. What else do we need? We need the density of the liquid. We're given the density of water is 62.4 pounds per cubic feet. So we're going to have 100 pi times dx multiplied by 62.4. Now because we're using pounds, we've already got gravity included, so we don't need to multiply that in additionally. And we need the distance traveled by the slice. So if this is the height x here, and we need to get this water all the way up to the top of the spout, what's that distance that it must travel? Well, the total distance from the bottom of the tank to the top of the spout is 36 feet. It's 30 feet for the tank and 6 feet high here. We're already at x feet high, so 36 minus x is the distance this slice of water needs to travel. So now let's multiply and integrate. So we have 100 pi dx times 62.4 times 36 minus x. And we're integrating x going from 0 to 15. So we're here, we integrate, plug in our bounds, and subtract. And just one thing to note here, when we're computing our final answer, because we were given density as 62.4 pounds per cubic feet, we were only given 3 significant figures there. So in our final answer, it wouldn't be accurate to have more than 3 significant figures. So we're going to round our final answer, in this case, to 3 significant figures, so that's 2,670,000 pi foot-pounds. Let's take a look at another. An open tank has the shape of a right circular cone. The tank is 8 meters across the top and 6 meters high. How much work is done in emptying the tank by pumping the water over the top edge? The density of water is 1,000 kilograms per cubic meter. Okay, an open tank has the shape of a right circular cone, so we're going to sketch this out. It says the tank is 8 meters across the top. That means the diameter is 8 meters, so we've got a radius of 4 meters here, and it's 6 meters high. And we want to find the work done in emptying the tank. And we can assume that the tank is full, since they didn't tell us otherwise. So we're going to let x, again, be the height from the bottom of the tank. And then x is going to vary from 0 to 6. Again, we need the volume of the slice of water, which is again a cylindrical slice, but keep in mind we have to find our radius for this cylindrical slice, because we have a cone shape and the radius on top is given to be 4, but at any given x value we have to find the corresponding radius. So we set up similar triangles. R is to x as 4 is to 6. So our radius is then 2/3 x. So the volume of our slice of water is pi times 2/3 x quantity squared times delta x. So that's 4/9 pi x squared delta x. And when we put that into our integral, 4/9 pi x squared dx. We also need the density of water, which we're given to be 1,000 kilograms per meter cubed. And since multiplying the volume and the density gives us a mass, we need to multiply by gravitational acceleration at 9.81 meters per second squared. We also need the distance traveled by this slice. This slice is x meters from the bottom of the tank, and the tank is 6 meters high. We need to get this slice to the top of the tank. So that distance traveled is 6 minus x for that slice. So then our integral is going to be 4/9 pi x squared dx times 1,000 times 9.81 times 6 minus x. So pulling our constants outside, moving our dx to the right side, we're here. We multiply through and integrate. Again, because we had gravity at 9.81 meters per second squared, we have 3 significant figures. So again, we're going to round to 3 significant figures here. And notice that the units we have are kilograms meters per second squared times meters. So this is a Newton meter, which is a joule. And let me just spell that to avoid confusion. Joule. Now let's take a look at some cable and rope problems. Typically the situation we have here is that we've got a heavy rope or cable and usually something heavy at the bottom of it, and this is being pulled up to the top of a wall or top of a well or top of something. So we're pulling this up and we want to find the work necessary to either pull it up all the way or halfway or something like that. So for cable rope work problems, we have 2 methods that we could use. Method 1 is to slice up the cable of the rope and move each slice up to the top, which is very similar to the tank problems that we were just looking at. In that case, the work is equal to the integral of the force on the slice at height x multiplied by the distance traveled by that slice. Again, very similar to the tank problems. Method 2 is a little different. Method 2 says at each height, find the force of the entire system and move it delta x units. Move it a tiny amount, delta x units, or dx in the integral. And this is similar to the work that we had moving particles at the start of the lesson. So in this case, the work integral is going to be integral of the force on the entire system at height x multiplied by dx. So there are two different setups here. Now for most of the problems, you could use either setup. When you have a rope, an elevator, or a non-leaky bucket, you can use either method. However, when you have a leaky bucket, you want to use method 2. And we'll see a leaky bucket by the end of the lesson. So let's start with an 80-foot rope that weighs 2 pounds per foot hanging off the top of a 100-foot building. How much work is done in pulling the rope to the top of the building? Also, how much work is done in pulling half the rope to the top of the building? So let's take a look at what's going on here. We have an 80-foot rope hanging off the top of a 100-foot building. So here's our rope. Here's our 100-foot wall. How much work is done in pulling the rope to the top of the building? Let's start with method number 1, where we slice up the rope. So we take a slice of rope of thickness delta x, and this distance x is the distance from the top of the building to the slice. So then our work integral is going to have the force on the slice at height x multiplied by the distance traveled by that slice. Now what's the force on the slice at height x? Well, this rope weighs 2 pounds per foot, and our slice is delta x feet thick. So the total force on that slice is 2 delta x pounds. And in the integral, that's going to become 2 dx. The distance traveled by this slice is x, because that's the distance to the top of the building. And that's how far we want that to travel. So that's x feet. And they said the rope was 80 feet in length, and so x is going from 0 to 80. So our integral for work is going to be the integral from 0 to 80 of 2x dx. We're multiplying the 2 dx times the x here. So that's 2x dx. And so we integrate and get 6,400 foot-pounds. Now part B says, how much work is done in pulling half the rope to the top of the building? Well, it's not going to be 6,400 divided by 2, because remember that this rope is heavy. So pulling the first half up is going to be harder than pulling the second half up. So we expect our answer for part B to be more than 3,200 foot-pounds, to be more than half of this. So let's take a look at how we can answer part B. Again, using method 1 still. So we're still slicing up the rope, and the force on the slice at height x is still 2 pounds per foot times delta x feet, so it's still 2 delta x pounds, or 2 dx, when we put it in the integral. But notice the distance traveled now is changing. Because as x goes from 0 to 40, the distance traveled is x. But for all the slices down in the bottom half of the rope, they're not getting all the way to the top of the wall. They're only traveling 40 feet up. This rope is 80 feet long, and we're pulling it halfway up. So that means there's going to be 40 feet of rope left. And so for all the x values from 40 to 80, the distance traveled is only 40 feet. So we have to separate our integral here. For x between 0 and 40, we have the same situation as above, because that part of the rope is being pulled up to the top of the wall. So that distance traveled is x feet. But for x between 40 and 80, these slices of rope don't get all the way to the top. They only move 40 feet. So their distance traveled is only 40 feet. So now we're taking the force on the slice multiplied by distance traveled for those corresponding x values. So our work is going to be the sum of these two integrals. Our first integral goes from 0 to 40, and it's 2 dx multiplied by x, so that's 2x dx for that integral. And then for x going from 40 to 80, we have our force of 2 dx multiplied by a distance of 40. And so we're here, 4,800 foot-pounds. And notice that is bigger than half of the 6,400 we had before to pull the whole rope. Let's take a look at this problem with method 2. Method 2 says, find the force on the entire system at height x, and then the distance traveled is that tiny distance dx. That comes from delta x in the approximation. So now we're talking about x being the length of hanging rope. And so for part A, x is going from 0 to 80 because we're going to be pulling the entire rope up the wall. The force on the entire hanging rope is going to be 2 pounds per feet times x feet. Before we had delta x as the length of our rope for the slice. Now we're talking about the entire length of rope. And so that's x feet of rope multiplied by 2 pounds per feet, so that's 2x pounds. That's the force on the entire hanging rope. So for part A, we want to take this force and integrate that, dx, for x going from 0 to 80. That's the same integral we had before, and that's 6,400 foot-pounds. For part B, since we're only pulling half of the rope up, we only need to consider the values of x when x goes from 40 to 80. Remember that x is the length of the hanging rope. It starts out at 80, and if we pull half the rope up, it ends up at 40, and that's as far as we go. So we're only including, in part B, x values from 40 to 80 with this method. Again, the force on the entire hanging rope is 2x dx, and so we integrate 2x dx from 40 to 80, and we get the same 4,800 foot-pounds as we got using method 1. So again, we're only considering these x values because the rope is only pulled halfway up. X starts at 80, and once we get to x equals 40, we stop pulling. Now let's take a look at what happens when we have something hanging from the rope. Here we have a bucket that weighs 4 pounds and a rope that weighs 2 pounds per foot are used to draw water from a well that is 80 feet deep. So now it's a similar situation. We have a rope that's 80 feet long, but now we have a bucket full of water at the bottom. The bucket weighs 4 pounds, and the water inside weighs 40 pounds. So we have 44 pounds hanging at the bottom of this rope. And again, we could use method 1 or method 2, so let's do both. And we'll start with method 1. We slice up the rope. Now, for x going from 0 to 80, just talking about the rope, this is the same problem we had before. But now at x equals 80, we're talking about this bucket of water. The force is 44 pounds, and the distance traveled is 80 feet. So this is not depending on x here. This is for only one particular x value, and so we don't need to integrate this amount of work. This gets added on to the integral that we have for x going from 0 to 80, and we get 9,920 foot-pounds. Now let's take a look at the same problem using method 2. Method 2 says take the force on the entire system at height x, integrate that multiplied by dx. So now we're talking about this bucket and water, and x is the length of the rope, which is also the distance from the bucket to the top of the well. We're not assuming this bucket has any length. We're just treating that at the bottom of the 80-foot rope. So x is the length of the rope, which is the distance from the bucket to the top of the well, and x is going from 0 to 80. So now, what is the force on this entire system? Well, we've got some force from the rope, and we've got some force from the bucket and the water. The force on the rope is 2 pounds per foot times x feet of rope. The bucket and the water weighs 44 pounds. So we have 2x plus 44 pounds. That's the force on the entire system when the bucket is x feet from the top of the well. So our work is then going to be the integral of 2x plus 44 from 0 to 80, and again we get 9,920 foot-pounds. It's the same answer. Now let's go one step further. Let's have this bucket leaking water. So now we have a bucket that weighs 4 pounds and a rope that weighs 2 pounds per foot are used to draw water from a well that is 80 feet deep, so it's the same situation. The bucket is filled with 40 pounds of water and is pulled up at a rate of 2 feet per second. But water is leaking out of the hole in the bucket at a rate of 0.2 pounds per second. Find the work done in pulling the bucket to the top of the well. So now let's just compare what we expect to get for this answer as compared to the last problem. The situation is very similar. We're pulling up 40 pounds of water from an 80-foot well. The rope weighs the same, the bucket weighs the same. Here, though, we're losing water as we pull it up. Because we're losing water, it's going to be easier to pull up. So our answer here should be less than the answer we had in the last problem. Keep that in mind. Also remember that we said when we have a leaky bucket, we must use method 2. Slicing up is not going to work. So we need to find the force on the entire system at height x, multiply that by dx, and integrate. So here we have the top of the well, we have our rope, we have our bucket, and we have our leaking water. Again, x is going to be the length of the rope or the distance from the bucket to the top of the well, and x is going from 0 to 80. Now we need to find the force on the system at height x. So we need to find out how much water is in this bucket at height x. We know it starts out to be 40 pounds of water, but we know that we're losing water as we lift the bucket. So at height x, how much water is in here? What's going to be the force of this bucket and water? That's what we need to find out. So to find the force in the system at height x, we need to determine how much water is in the bucket at height x. Well, what do we know about the rate at which the water is leaking? Water is leaking at a rate of 0.2 pounds per second. We also know that the rope is pulled at 2 feet per second. So we're losing 0.2 pounds for every 2 feet that's pulled. Right? 0.2 pounds per second, 2 feet per second. So every second, we're losing 0.2 pounds and traveling 2 feet. So we're losing 0.1 pounds per foot traveled. So when the bucket is at height x, that means it's x feet from the top of the well. It has traveled already 80 minus x feet. So it has lost 0.1 pounds for every foot that it traveled. So it has lost 0.1 times 80 minus x pounds of water. It started out containing 40 pounds of water. So the bucket contains 40 minus 0.1 of 80 minus x pounds of water at height x. That simplifies to 32 plus 0.1x pounds. So when the bucket is at height x, meaning x feet from the top of the well, it contains 32 plus 0.1x pounds of water. Okay, so now what's the force on the system at height x? Well, the force on the rope is 2 pounds per feet times x feet of rope. The force on the bucket is 4 pounds. And the force on the water is 32 plus 0.1x pounds. So adding this up, this gives us the force on the entire system at height x. And so that's what we're going to be integrating. We simplify, and that gives us 36 plus 2.1x. And so that's what we're integrating from 0 to 80. And so we integrate and we get 9,600 foot-pounds. And in fact, this is less than the 9,920 that we had in the last problem. And with this, we'll conclude our lesson on work.